Quite afternoon. Welcome everyone. And so during the program, and then we try to have extra seminars between workshops. So this is one is by Professor Zhang from Nottingham University. He's going to talk about a convexity-based method for approximation and interpolation of input functions. Okay.
Thank you very much. I would just like to thank Xue Chen, Ke Chen, and all organizers of the program for inviting me to give a talk on this. This is a joint work with Elaine Crooks and Antonio Orlando. So you will see something familiar as well in this, but I don't use the way people deal with the operators. So I'll have a quick overview about this. I'll talk about motivation first, then the method. I call it compensated convex transforms. I'll give the definitions and some basic properties. Then I'll use such transforms to define approximations for sampled functions, which can be sparse, sparse functions, or what we call the in-painting and other things. So the main mathematical bit is about the so-called Huasdorff stability about the average approximation and the error estimates for in-painting like functions. So I will also show some prototype examples and numerical experiments. Prototype means you just compute these things explicitly by hand and use Mathematica to plot your results. So numerical is we write numerical schemes for compensated convex transforms and just realize the thing. All right. If I have time, I'll give a quick sketch of the results I claimed here. If we don't have time, then I'll just skip the last bit. All right. So the motivation is mostly for a quick review of some known methods for approximation and the interpolation methods dealing with sampled functions, which means there are holes or scattered data that you try to interpolate. So there are quite a number of methods, but I'll not just read through all of them. Radial basis function, this is for scattered data, nearest neighbor interpolation, and thin plate spline, and Delaunay triangulation. There are many PDE-based methods. So, but the observation for those, that's the motivation to look at for the mathematical side, many of these are based on numerical experiments. The statistics of graphs say this is numerically based on some pictures, what this thing can be done. The rigorous error estimates, many of these do not tell you, given a situation, what your method will be with the known the function. Suppose you know the regularity of the function. Also, stability justification, robust. This is a numerical experiment sometimes. But this means stability, which means if you take two samples which are close, whether your output will be close or not. So this is the meaning of stability. Also, sample types. Sometimes you get the level sets. Sometimes you get this scattered data, and sometimes you have a whole to be inpainted. So these are different type of things. This method defined to apply to all of this. There are no regularity requirement of the set involved. Some methods has regularity restrictions on the set, like the AMLE requires smoothness of the boundary, and the output are smooth functions. In fact, this is the latest mathematical result. All right, let's look at the method we claimed. So we define two types of approximations. One is Lipschitz continuous, and the other is C11. We can only do that, nothing beyond this. We can't get the C infinity method. The advantage is this method can apply to general closed sample sets, finite sets, level sets, edges, compact sets, and in-painting sets, which means the complement of an unbounded set. We call it an in-painting set. So for bounded continuous functions, we can prove Huasdorff stability. So we can prove some kind of error estimate as well. So then we'll just show some explicit prototype examples. There are some possible applications for in-painting, CAGD, and so on. This is arguable whether how it's okay. Now let me introduce the transform, which is rather easy to define. It doesn't involve anything complicated. So for simplicity, suppose we assume the function to be a bounded function. Otherwise, it's at most quadratic growth or something. If we just want to do this in one go, so the method is for your function, you add a weight is the parameter times the norm, the Euclidean norm squared. Then you take the convex envelope of that, then release the weight afterwards. So this is the approximation from below. You can also do this from above, which you need to convert this a little bit to get the upper transform, which means your approximation lies above the function. This is below the function.
So if f is a convex, you will get the same.
Yes, if f is convex, there's no effect for the function. But you concave, that you have some, but you don't have effect on that. But in general, when we deal with data, we don't know anything about this. All right, let me look at alternative characterizations which get to some familiar territory we can view this as semi-convex or semi-concave envelope of a given function. That means semi-concave is the which one is smaller, which is the larger. This is the largest semi-convex functions with linear modulus. The traditional name is called that, linear modulus. This is you take the semi-convex envelope from below, you get this. You get the semi-concave envelope, you get the other one. Also, it turns out, it's in fact first pointed to us by the referee that this is in fact the mixed Moreau envelope. That means you apply Moreau envelope, lower Moreau first, then followed by the upper Moreau. Well, the other is the other way around. You take the upper Moreau first, then the lower Moreau. Where I define Moreau envelope as this. I don't write as 1/2 mu or something. It doesn't matter. Anyway, this is a positive number, right? So in the 1990s, the mathematical morphology community already know that if you use the Moreau weight, if we call it that, as the structure element, you can define openings and closings for a given function using such a structure element. But the thing is, why such an obvious thing has not been developed further? That's the question. The challenge is this: when you use Moreau envelope to do smoothing optimization, to calculate Moreau envelope is quite a challenging thing. And if you do the composition of two Moreau envelopes, it will be very hard to calculate in general, right? However, if you know, sometimes you just, for simple models, you can just use the convex envelope for simple configurations. That can be much easier to calculate. Therefore, if you do it in one go, interpret it in a different way, you might get some more insight about this. So try to analyze functions using this definition is quite a challenge. But we usually analyze using the direct definition. My original motivation was from this translation method when we deal with this quasi-convex envelope in the vectorial calculus of variations, where this kind of calculations came up repeatedly. Then I thought maybe that might be a thing to deal with by itself. This thing appeared several times in my calculation. So that's the reason, my motivation at least. All right, so these are the alternative. Also, there's the Lasry-Lyons regularization. Well, these two must be different in the definition of Lasry-Lyons, because they want a C11 approximation. If the two parameters are the same, then the function is not necessarily C11. Therefore, in the definition, they specified that these two cannot be the same. They didn't define it for the same parameter. But I call it critical. Therefore, I call it this is critical last Rayleigh. They didn't define this though. All right, there are some simple properties, but which are very useful when you deal with this. The upper is from above, the lower is from below. Also, there's an ordered property. That means if a function is below the other, their transforms preserve the order as well, both for upper and lower. The upper doesn't give you the opposite. It's the same. And also, if both transforms can be defined, then you can use this to get from one to the other. There's another useful property which is called the translation invariance, which means you can change the center of the weight to any point. Then you do the convex envelope. Then you just release it by using this difference. The reason is the convex envelope is affine covariant. You add an affine function to take the convex envelope, you can pull it out. So then, if you expand this, you can cancel that. So this is easy to see. Therefore, when we calculate, we can move the point to 0 to calculate things. So Lipschitz continuity in one sense is these things you can have such an estimate. Regularity means the mixed transforms. If you do the lower followed by the upper or whatever, the function, the resulting function will be C11. It doesn't matter whether they are the same because these two Moreau envelopes are involved in one. If you insist on calculating it using Moreau, that's what you get. These are simple properties. Also, these functions does not look at L infinity or L2 or whatever. It deals with the lower semi-convex envelope of the function. So if the function is not necessarily continuous, the lower transform is the same as the lower transform of the lower semi-continuous envelope. The upper is the other way around. There's locality property by estimate. So suppose f is bounded, and if we define the oscillation of f as sup subtracting inf, then the lower transform at x0 is the local convex envelope in the ball with the radius r, which means if you use the convex combination definition of the convex envelope, you can restrict your points in the ball. You don't, because remember, convex envelope in general is not local concept. You can easily define functions where the convex envelope involves point as far as you can design. Well, the radius is the square root of essentially the oscillation of f divided by lambda, which means if lambda is large, the radius will be small. So it's a local thing. As long for a bounded function, as long as lambda is positive, it becomes local. It's easy to show Moreau envelope is also local. You can estimate it rather easily. That's a local concept. So Now let's talk about the so-called touching set, where the lower transform touches the function. Because of this, if f is not continuous, we can only touch the lower semi-continuous envelope. The touching set has an epsilon. Is also local. Given any point, the point is in the convex envelope, the convex hole of the touching point within in a ball with radius r. That means it has the touching set has a density. It will touch the graph in a dense fashion, which depends how dense depend on lambda. This is the general estimate. It doesn't specify to any specific function. So in general, for a bounded function, the lower upper transforms are both Lipschitz with the Lipschitz function 8 square root of m lambda something. It's not hard to establish. All right, tight approximation. This is different from Moreau now. Moreau envelope is not tight. If you calculate, there are very limited situations you can calculate Moreau envelope explicitly. For the absolute value or modulus of x, we call it, the Moreau envelope, if it's the Huber, what's it called, regularization or something. If you look at that, it's not tight. It does not attach to the original function. So this is tight, which means if you're in a neighborhood of a point, f is C11, then for large lambda, the upper and lower transforms agree with the original function. So they attach to the graph. So this is the square distance function of a 4-point set. So we can somehow explicitly calculate the lower transform. So you can see this is the part, the function, the lower transform changes the value of the original function. Outside this agree with the original. So this is a tight approximation. It alters the function near the singularity. Otherwise, it's the original function. Well, this is the mathematical result. But when we calculate that, I haven't tried to calculate Moreau envelope for that, though. It's rather easy to calculate the lower transform for that, but not easy directly. Yes. Explicitly by hand. I mean, these are mathematical plotting. So it's not from a numerical. Of course, it's numerical when it plots. You need to set how many points you allow. That's the only thing. You load in the formula, then let it plot. So this is not a very challenging case even. All right. So now this is already okay. This is the definition of it. So given a sampled set, K is either compact or complement. It's a complement of an open set. This is to model the in-painting case. Then we define two functions. We assume m is a number bigger than the supremum of the absolute value. Usually in practice, we set m to be 5 million or something to make sure it doesn't touch. You just blindly do that. You don't need an initial guess, for example. You just set it very large. That will be enough. So one has a very high ceiling. This has a very low base. That's what intuitively outside K, what you define. Then we define the so-called average approximation with scale lambda, which is just the average of the lower of the function with very high ceiling and the upper from another function with very low base. I will show you a simple 1D picture to see what's going on. But if we can smooth this a little bit, to take the mixed transform, then take the average. This will give us a C11 approximation. But this is Lipschitz. But the Lipschitz constant can be very bad, depending on how large your lambda is and how good the function is. All right. So now this is a picture, a cartoon of the transforms. So now we hold 1, 2, 0, 1, 2, 3 as our set in 1D, and we just take the values of this function x squared over 4. Then we take m to be large so that this doesn't touch the ceiling. Then we do the lower transform. It will hold such points and give you the parabola upwards because the outside is kind of, you imagine this by holding something that you blow the thing from below. With the force, the larger the force, the curvature will be bigger. I forgot to mention that lambda has a specific geometric meaning. It's the curvature bound allowed in your transformation. You set the curvature restriction, then you get this. It's not, it has a specific geometric meaning. So you see, the lower give you this, the upper give you that. The average is simply this affine interpolation in this case. It's a very simple thing. Then people can say, well, this is in 1D, this is easy to construct by hand, right? But when you imagine you have your scattered points in the plane, then you can't easily do that, right? So because you see, if you have an algorithm to calculate the upper-lower transform, then in the definition you just do blind calculations. You just run things without knowing exactly. You don't need to know that. It will give you the approximation. So this in higher D, in fact, this can be the piecewise affine approximation by Delaunay triangulation. But the thing is, when there are degenerate cases in Delaunay, you have to decide what to do the interpolation, right? But this one will automatically give you an interpolation by itself. So these are again calculated explicit approximation. Suppose on the 4 corners of a square, you just define 1 and -1 alternatively. This is a degenerate Delaunay case. 4 points are on the same circle now. So this method doesn't ask you to design anything. It's just introduce another point in the middle and give you that. If you have more points defined on the circle alternatively, it will just hold such points and go up and down by itself. These are explicitly, remember, such approximations are only considered in the convex hull of the set. We don't consider what happens outside the convex hull. So now I mention what do we mean by the Huasdorff stability, the meaning of that. Suppose F is bounded, and you have two closed sets which are close under the Huasdorff distance. This is the definition of Huasdorff distance. Suppose F is bounded uniformly continuous. We just give a priori that suppose F is continuous, what's going on then? At least then we can see as long as the Huasdorff distance are close to each other, then these transforms will be close to each other. So that means if you give two sample sets, like the salt and pepper, you get two. If you apply it twice, you get two different sample sets. You might have a statistical density, but you don't know whether they are the same or not. Now the question is whether your output are similar or not. This is a point-wise estimate. That every point the values are close to each other. So this is what we call Huasdorff stability. But there's a technical issue. When we do in painting, the set we know is an unbounded set. But this doesn't matter. In many situations, the Huasdorff distance for unbounded set can be very close, right? If you think about complement of two samples, you cut it in two different shapes, the complement will be close. Okay, so therefore, the Huasdorff stability, I will just mention how we deal with that. But if I have time, I will give a sketch otherwise. So the lower transform can be rewritten as the upper transform of something else. The upper transform is written as the upper transform subtracting something. This is the characteristic function of the sampled set. So we can always rewrite this as such. Now, the problem of the average transform can be reduced to the question of the Huasdorff stability of this mapping. If you have a function g which is bounded below by a positive number and above by another, then you multiply g with the characteristic function of k. Then you talk about whether this is Huasdorff stable, because then that implies all the rest are okay. So the theorem is a rather technical statement. Suppose omega is a continuous majorant of the modulus of continuity of square root of g. This is for simplicity. Then we have such an estimate. The upper transform is bounded by Huasdorff distance with some constant in front. And here is the modulus of the the continuity of square root of g, but applies to the distance, Huasdorff distance. A simpler version is for, suppose g itself is Lipschitz, then we have such an estimate. It's a number times the Huasdorff distance. This is the Huasdorff-Lipschitz continuity. But there's a balance of this, because we prefer to have large lambda and large m. Then you need this to be closer to get that close. That's the problem for such a it's easy to imagine from this cartoon picture. The bigger lambda is, the lump will be higher and higher, then you have less Huasdorff stability. All right, so error estimate is we wish to find an estimate of our average approximation and the original function f under certain regularity conditions of f. We don't know what f is if we cut a hole, but at least we know if f is continuous, what happens. So we define two distances. One is called Euclidean density radius, which is simply the distance from the point to the set. And we define the convex density radius is the radius such that x can be represented by a convex combination of points in K whose distance to x is less than or equals to r. So this is the convex. This is bigger. This is bigger than the Euclidean distance. So don't worry about the example of the details. It simply says that suppose the set is the square plus 4 points. So at this point, the Euclidean distance is just that. But the convex radius is that, because you require this point to be in the convex hull of your original set. The only possibility is to use this point and that point. Therefore, the radius is quite large. So these are different concepts. But we use this to estimate, though. So now we estimate, but to make it neat, suppose K is compact, then we, outside the large ball, we define the function as a constant. We define the function as a constant. You can simply set it to 0, then theoretically you can use extension method to get it to be Lipschitz or continuous or whatever. So then we use the modulus of continuity twice. We use such a modulus of continuity of f which satisfies such an inequality. If you look for books with that, there are majorant satisfying this. So we use such a thing, then we apply it twice. So the estimate is this. The modulus of continuity inside is the convex radius plus some weighted a and b's with lambda and square root of lambda. But for Lipschitz continuous functions, it gives you a very neat estimate depending on lambda and the convex radius at the point. All right, but this looks rather technical, but let's look at the picture as well. But before we continue, I should remind you that these approximations are not necessarily interpolations, because you take a lower transform is not necessarily attached to the function everywhere. It's just an approximation. We have the rate though, but that's later. So this RC, in the case of inpainting, if we define dx to be the shortest length of the line segment connecting x and k, that's the bridge from one side of the bank to the other. This is the shortest distance. That's, we call it d. This is bigger than RC. So we also have the asymptotics, which will be independent of approximation parameter. Asymptotically, for a uniformly continuous function, the error is bounded by the modulus of continuity only, with the whole, how big the gap is. For Lipschitz, it's just the Lipschitz constant times the convex, what we call it, convex radius. All right, to make it the estimate, as I mentioned earlier, this is not necessarily an approximation, but in the part of the set where we know the value of f, we have such an estimate. From below, this is the estimate, how far the lower transform is from the original. And for Lipschitz continuous functions, we have such an estimate. So that means we have a very good approximation, even it's not an interpolation of the point where we do not take inpainting. So we don't hold the values outside, we just blindly apply the compensated convex transforms. So therefore, we have such an estimate. This is on comparing with others, but it's difficult to find such estimate. So this is from Chan and Kang. The estimate is use Laplacian in a subdomain of the omega. So under the Dirichlet condition, so m is the maximum of the Laplacian in the whole domain. That's m. Beta is the so-called minor diameter of any ellipse covering the inpainting domain. Is this accurate? I mean, my statement is the same as what they said. All right. There are another inpainting method, particularly for level sets, called AMLE. Actually, Antonin told me that. I didn't know that before. It requires sampled set to be isolated points and Jordan curves. That's the mathematics in it. When they do the inpainting, they just apply to the sampled level set. But in the theory part, this is the requirement. But the later development suggested that the infinity Laplace in 2D gave you a C1 alpha function. So it's a smooth function. So it won't preserve jumps, say, for example. It's C1 alpha. All right. Now this is a hand-painted picture. So to indicate what's going on here, this is the beta, the radius, I suppose. This is the beta omega. So the minor diameter, that's this, of the imprinted area. This is d omega. The large is the gap along the river, that's d omega. So they asked the question whether we can use d omega. That's what they asked. So in the result, we can use d omega to measure. So remember in the earlier page, the asymptotic is bounded by d omega. Otherwise, you tune lambda, it will be as close as d omega as you, because we only assume f is Lipschitz, but which Lipschitz function we don't know. Therefore, this is the best you can get, right? If you say this is the one, I can deliberately construct another Lipschitz extension to make yours not exact. So the worst error is bounded by this. It's for every x in that river, though. If any x in the river is bounded by the gap depending on x. This is the length. So this is the error estimates. At least this mathematically it's reasonably solid. So this one, I can't do it for Euclidean. I use the parameter to write the plotting in Mathematica. This is how the method approximates two straight lines overpassing each other in 3D. So if I allowed to use the parameterized plotting, it gives you this. This is, suppose you have a circle here and another on an annular domain. You try to do the interpolation or approximation. So the result is, as long as lambda is large enough, you have just this part of the cone or something. But it is known in the 1950s that if you try to solve the minimal surface equation in 2D on the annulus domain, if you assume the value here to be a constant, say 0, if you make the inner value large enough, the solution cannot be regular. It's singular. The reason is there's an estimate. Given the value in the outside, the solution has an upper-lower bound purely based on the outer boundary. Therefore, you deliberately move the inner value outside the range, then the solution cannot be smooth. The reason for that is when people try to smooth total variation method using that. The thing is, after a simple change of variable, this is the minimal surface energy. Therefore, that imprinting need not to be smooth itself. So, but for this, it doesn't matter. You just take the upper lower. It always exists, and it's always Lipschitz anyway. So this is the calculation of that is very easy as well. It's rather symmetric to calculate the upper lower transforms. All right. So this is another prototype which I mean by explicitly calculated. In this case, my set K are just these two lines, segments. the sampled function are 2 of this. So then the resulting average what we call the approximation will lower the value in the middle a little bit. It's not exactly the same, but it can go cross to preserve this wedge somehow, in some sense, depending on how you set lambda to be more accurate. So if you want to inpaint this cross the black and white, there's a restriction. If the height is shorter than the width, you can somehow inpaint cross the gap to rust. When you do the inpainting, it also modifies the jump. But if you make lambda very large, the jump will be closer and closer to the proper jump. So, there are other, but they are not always nice. So now if we change the set to on the rectangle, on these 2 sides, I just set the value to be 0. On the side, I just do the 1 over norm x squared or something like that, modulus of x squared. So if this part is longer than that, then I can inpaint cross to essentially keep the hut right. It's more or less like a. But if I stretch this length, it will collapse to the middle. So it won't give you a nice things forever. So this is explicitly calculated. But I saw a numerical result for minimal surface. Under such a boundary condition, it gives you something similar to this. It doesn't hold cross the ridge to connect from one end to the other. It will collapse as well. I remember it's by Kempf some years ago, but I couldn't find the picture I downloaded from the internet. Well, now this is some numerical things about level set, and I will show the defect of such approximation. So if you have this piecewise defined function using some maximum, min, and so on, then suppose you take the level sets like that, then when you take the average transform, then you have some small steps generated by the method. In effect, this is how you get it. It should go along the ridge to connect from the bottom to the top, but it will somehow generate some steps instead. Therefore, numerically, you can see those. This is from the method itself. Therefore, you need to add something, other information to get this rectified. So, by the traditional Frank's test function for interpolation, at least this is very smooth. So we can see the results are very close. For a jump function, you can see you can have the jumps. It's a reasonable approximation for this jumps with 4 pieces. We take level sets of this and reconstruct. All right, this is a less. This is I saved from the screen of MATLAB. The function is defined as such, but it doesn't matter. If we view the image, we can see what the function is. So the function is this. It has four ridges and 4 valleys. Then, if we use 5 contour lines to reconstruct, you can see the steps. But if you allow to add edges, that means if you allow to add the values on those as well, like what Jia did, Wickert did some time ago, then you can make it very nice if you like. All right. Now I can select either I use ridge or valley to reconstruct, which means I require the values on those as well. Then at least in terms of the so-called PSNR, it's 61. But if you only use the valley information, you only get 36%. It depends on the curvature of this, in effect. The smaller the curvature, you have less effect. So the question is how to extract such information. That's a different matter. All right. So now I will just look at some level set approximation. I forgot to write down some PSNR thing because it doesn't matter now. All right. So this is a bit similar to the Castell-Merau result. Their picture has also such flat areas using AMLE. So I looked at the internet and see what people do. Actually, I don't know what to do. There's a question about connectivity I learned. So then I just try to see what we got for connectivity. Mathematically, we can prove somehow if this black thing is perpendicular to the part which covers the small strip, then you can go cross without any trouble. But there's another condition: is this length needs to be longer than the gap. It doesn't matter how far the gap is. It depends on how far this part is. If you want to make it long, you need to cover more. Then you can calculate explicitly the upper and lower transforms and show the resulting functions are just this. This is just black-white. This can be proved by explicit calculations on prototype. It doesn't matter about the angles. It doesn't need to be horizontal or vertical. You need this to be perpendicular. That's the key. All right. I think I started late, but I will finish in 1 minute. So then we can play with colors or something to see whether it does. This is salt and pepper. So I don't do any learning. Therefore, I don't know what's behind. I just use mathematics of the given data, and no learning at all. All right, so you randomly put some stripes, then you can find something behind. But the thing, as I observed earlier. If this is perpendicular, you can see there's less trouble. If it's not, this is 45 degree, then you can see where the trouble is. Right? If you compare with the earlier exercise, I can prove this can go cross. But if there's an angle, then it cannot. So that's I don't claim whether it's good or bad. This is what we can prove. That's all. Not this, of course. You can't prove you don't know the function at all. For prototype, we can prove that. All right. There are some reference for this work. There are some other applications. Elaine will talk about something else about the medial axis, because that is related to the shapes. There's one of. All right. I think I should stop here, because after that I left this deliberately at the end, depending on whether I have more time. So I will just stop here. But I shouldn't forget to say thank you or something at the end. Okay, that's all. I think I finished on time. All right.
In practice, how easy is it to do numerics with this?
It's rather simple. There are at least two different methods. They are all blind, but they are like the PDE method, finite difference. Therefore, we have to stay on grid points. That's the trouble. It's not like in CAD, you only need to know the sample point. You have a list of locations, then you run from there. Like the mesh generation thing, you only need the list of the locations, then you do the meshing. But if you require the grid points, it can only go as far as graphics, but not for the general CAD or CAGD rather requirement.
Where you compute your whole parabolic envelopes?
No, this is local. It's not a global business at all. For one scheme, we can predict how many iterations it will stop. It gives you the accurate, for Moreau envelope. Of course, you need to control the.
But for Moreau, you have a dynamic principle.
Yes. For Moreau, there are easy numerical schemes which will stop in finite time because it's the mean. If you say the mean already runs through the whole domain, then you stop, right? It's the minimum of the dimension. That's how many iterations you need. The worst case. Also, you can do direct convexification, but that's less accurate. For singularity extraction, it doesn't matter. This is local. You don't need a lot of iterations. But for reconstruction, that method gives you some extra things, artifacts, and so on. Many symmetric functions can be calculated explicitly by hand. So the thing I showed on the screen are not the most exotic, though. There are more complicated things like corners and so on. You need to justify your method the method can extract intersections of surfaces. You need to show at the intersection your transform is positive. Outside, at least when the parameter goes to infinity, it will go to 0. So that means you do need to to have a reasonably good control to prove such things. But if you use the Moreau envelope definition, it will be rather difficult because you don't know the first Moreau envelope exactly. Therefore, you take the composition, it will be even more challenging. The convex envelope business is much easier way of doing it. That's Thank you.